Okay, so good evening, everyone. I'm Calvin Joseph, and today I'll conduct your week 8 problem solving and doubt clearing session for the course Controlling Tuning Methods in Switchboard Power Converters, which was taught by Professor Sandro Kapat. So, today we will see these things. So, today we'll be discussing about the accurate small signal modeling for current mode control. We'll be discussing about what is the controller design when we are doing current mode control for a boost converter. We'll talk of what is a practical current sensor, and also we will discuss about average current mode control. And we'll also solve some questions. Okay, so let us start. So today is week 8. So we are doing current mode control. So for a buck converter or for a boost converter, what is the transfer function in current mode control? What is the transfer function? Under current mode control. Any idea?
GVC of S.
Okay, so you have GVC of S, which is actually your V output of S by I control of S. Okay, this IC of S is not your capacitor current. This IC of S is your like a command current signal which you want. Okay, this is your IC of S. Okay, so now, what is the order of the transfer function? Like, how does the transfer function look in terms of poles and zeros?
First order.
Okay, it's first order. And for a boost converter, it will look like this. It is R, let us say, this one KTC into 1 minus S upon omega RHP into 1 plus S upon omega ESR upon 1 plus S upon omega P. Okay. So, what are these things? If you see, this is actually a numerator has 2 zeros and denominator has only 1 pole. So, it is actually like an improper transfer function. So, what actually is there is like this is an approximate transfer function. There would be some poles over here. There are certain additional poles over here which are very high frequency. So they have been neglected. Okay, these poles have been neglected. Okay. So we are approximating it to be first order. Now these things are very important for you guys since you'll be giving the exam. At least these values of KTC, omega RHP, omega ESR, omega P, you have to by heart and go. Because there is a certain amount of marks for recall, right? Certain amount of marks for recall are there in your final exam. So certain things you have to by heart and go. And the assignments also, you solve the sums very carefully and you should remember them because many questions will come similar to the assignment. That is the pattern which is followed by NPTEL. They have like recall, then something open and based on assignment question. Like that, they have the categories. So assignment based questions have a lot of weightage. Okay. So you follow that accordingly. Hmm. So now in this transfer function, which you have to remember, your DC gain for a boost converter is given by R into 1 minus D upon 2. Okay, this is your DC gain. Similarly, your omega RHP, that is your right half plane 0, that is actually given by R into 1 minus D squared by L. And your omega ESR, that is a pole, no, sorry, the 0 which is introduced due to the ESR in your capacitor, ESR in your output capacitor, that is given by 1 upon RC into C. And your omega P is actually 2 upon R plus 2 RC into C. Okay. So there are certain cases where your RC is negligible. In most cases, it is negligible. So what we take it as RC, we approximate to be 0. If it is asked in the question, you assume RC is approximated to 0 unless it is clearly specified. Okay. If that happens, then this pole will not be there. Sorry, the 0 won't be there, and your omega p in that case will become equal to 2 upon RC. Okay, so again repeat, these are important things which you have to remember. These are important values which you have to remember because questions come on these. Now, there were certain assumptions which were made while we were doing this modeling of a first order transfer function. One is, as we had also previously told, suppose this is your time, okay? And this is your plot of your inductor current. Your inductor current is given like this. Okay, your inductor current is given like this. Hmm? This will assume to be periodic something. And we are in the modeling which we are doing, what we are doing is we are trying to find the average value. We are modeling what will be the average value because if you remember, we are averaging over the switching period. So we are finding out the average value. We are not finding out the instantaneous value. Okay. And also we assume that this ripple is small. So this is known as your delta IL. Okay. So what are the assumptions? We have assumed that your delta IL is much, much smaller than your IL average. This is one assumption, which in some cases it is true, in some cases it is not true. And when we are doing the current mode control modeling, what we are doing is we are saying that this signal over here, the peak, this is your I command signal, IC signal. So we are assuming that your IC is approximately equal to your IL average. But that is not always true because you have your ripple is also there. So that's why in those cases your modeling is not accurate. Now when you so to overcome this limitation, what people have come up is with two methods for modeling your current mode control more accurately. Okay, there are many other advanced sophisticated methods, but Sir has spent time on two methods which we will again look into, and those questions also are important. Hmm. Also, one more thing is there is something known as a compensation RAM. If you would remember, in the lectures where Sir talked about fixed frequency and variable frequency, Sir was saying that in variable frequency, you do not need compensation RAM, but peak current mode control requires compensation RAM when your duty is greater than 0.5. You require it. In valley current mode control, you need compensation RAM when your duty is less than 0.5. Okay, so when we did the modeling using and when we obtained the first order model, we did not even consider compensation RAM. So that those all also we will include in the following derivation, which we'll proceed to do. Okay. So till here, any doubts, any queries? Okay, and this day is 16. So on this Friday, 19th, I'll be conducting my session, and Teja will be conducting his session on 20th. That is the Saturday. Okay. So we are kind of preponing our sessions so that we will do week 9 this week itself. That is this Friday, Saturday. And week 10 we will do on 22nd and 23rd. Okay. Because the next week we would not be able to conduct sessions. That's why we have talked with NPTEL people and we have asked for preponing our sessions. So Friday and Saturday will work for you guys, right?
Okay, sir. So on 29th and 30, no sessions. Is it like that?
No session would be there. So we'll be covering the week 10 on 22nd and 23rd, and week 9 on 19th and 20th. So that you guys would have the videos recordings also will be available by then. So it would be helpful for you guys to even solve the assignments. So we are not delaying it, we are preponing it. Hmm. Okay. So I'll start with the modeling. So we are trying for a more accurate model using current mode control. So what do we have? We have our, this is your reference IC of t. Okay. Now, to this reference, we actually subtract a compensating ramp, that is, which has a slope of minus MC. Minus MC. Okay. And you have your current going here, coming here, going here, coming here. Okay. This is your slope M1. This is your slope minus M2. These slopes are also very important. You need to know what is the slope for a buck converter, what is the slope for a boost converter. Okay, if you have any doubts regarding that, you can ask me as well. Okay, and what is your duty? This is your d of t, right? And this is your 1 minus d of t. Again, over here, try turns on, switch turns on, and over here turns on. So this is your d of t. Okay, so what happens in this arrangement is your switch is always turned on at this point. This point, your switch is always turned on. Turns on like this. But whenever it hits the peak, it will turn off. Whenever it hits that value, it will turn off. Okay. So that is why the falling edge of your gate signal Q, that is being controlled. That's why this is known as trailing edge. Trailing edge modulation. Okay. Because the rising is fixed, but when it is falling, that is depending on your control. That is why it is known as trailing edge modulation. All right. So this is your set pulse. It gives you a set pulse when to turn on, when will the inductor current start rising. So, and what is your average value? This line, this is your IL average. So what do we want to find is, we want to find a relation between your IL average and your IC of t. We want to find the relation between them. So how do we do? Anyone has any suggestions or has seen such videos? How has sir done it?
IL equal to IC minus
Okay.
MC into D.
Yeah. So let us say this is your peak point. This is your I peak, right? This point is your I peak, right? So your I peak, let me reduce its size. So your I peak is actually equal to your IC minus MC into DT, right? Because here it was IC, then you're subtracting minus M, slope is minus MC, and the time is DT. So your I peak is equal to IC minus MC DT. Also, your I peak is your IL average plus delta IL by 2. because this is your IL average. This entire thing is your delta IL. This much is your delta IL by 2. Okay. So this we got. So IP is equal to IL plus delta IL by 2. So in the first approach, we only consider the rising slope. So your IP is equal to IL average plus M1 upon 2 into the time period, that is dt upon 2. Because we are only focusing on the time when it is going from, that is from this point to this point. So that is half of this time dt. That's why it is dt by 2. Okay. Hmm. No. I made a mistake. You are doing delta L by 2. Okay. So you're doing delta L half of current ripple. So current ripple is M1 into dt and by 2. So this factor of 2 will not be there. Sorry. This factor of 2 is not there. Okay. Because your delta IL is equal to M1 into dt. So your delta L by 2 is M1 upon 2 into dt. Hmm. That is fixed. Okay, so you got your I peak, both I peaks you got. Now what you have to do, you have to equate them. So you have your average IC minus MC dt is equal to average IL plus M1 by 2 into dt. Hmm. So now what is done is we add what is known as perturbations. Furthermore, this we should not use capital D, we must use small d. So what we do is we add perturbations IC plus IC tilde, IL is equal to IL plus IL tilde. MC, also you can write MC is equal to capital MC. It should be small MC. MC equal to capital MC plus MC tilde. And M1 is equal to capital M1 plus M1 tilde. So when you substitute that, you will get IC plus IC per term minus of MC plus MC per term into capital D plus D per term T. Okay, so your D should be replaced by D plus D per term. And we will consider your MC per term is 0. So we can neglect that. We can neglect this, right? So this will be equal to minus MC into D plus D per term into T. That is equal to your IL plus IL per term plus M1 plus M1 per term by 2 into D plus D per term into T. Okay. Now we equate this as IC minus MC dt is equal to IL plus M1 upon 2 into your D into T. These are your DC terms. Then we equate the AC terms. We write IC tilde, this equal to IL tilde minus of, we take this side, so it becomes plus MC D tilde T. And you have your plus M1 tilde dt by 2 plus M1 into D tilde by 2, 2t. Okay. Any doubts in this part? Hmm? You guys are very silent.
Okay, sir.
Not sir.
Okay. Yeah. I don't like silent treatment. Okay. Yeah. So let's continue. So we have our I control per term. This is your IL per term plus MC plus M1 upon 2 Okay, what a blunder I made. Sorry. T is over here. T is in the numerator. Into T per term plus M1 per term by 2 into dt. Okay. So now what do we do is we want to write d tilde as some fm into your IC tilde minus IL tilde minus something like this. We want to write in this form. So what do we do is take this d per term in the left hand side, or we just shift these things all to the right hand side. What we will do is we'll write mc plus m1 upon 2 into t into d per term, that is equal to your IC per term minus your IL per term minus dt upon 2 into m1 per term. So for d per term is equal to 1 upon mc plus m1 upon 2 into t into your IC per term minus your IL per term minus dt upon 2 into your m1 per term, right? So we write it as d tilde is equal to fm into IC per term minus IL per term minus dt by 2 into m1 per term, where your fm in this modeling technique is 1 upon mc plus m1 upon 2 into t. Okay. So for a buck converter, what is your m1? Can you tell me?
Vn minus V0 by L.
Okay. It is Vn minus V0 by L. So what will be your M1 per term?
Vn per term minus V0 per term by L.
So it is Vn per term minus V0 per term by L. Hmm. So we are considering that your inductance is fixed, right? We are not considering any perturbation in the inductance. So this, what do we do then? We substitute this thing over here, and then you will get in terms of Vn per term and V output per term, right? So these are the steps for the first method. For your first method, which is also known as your Middlebrook method, Middlebrook approach, it is also known as. Okay. So let's go for the next method. Second method. So in the first method, what we did, we found our I control, right? Sorry, we found our I peak is equal to I control minus MC dt, because we are finding out this point I peak. I peak is equal to IC minus MC into dt. This is fixed. This is the point which we are modeling at. Now, what we do in our second method is we are considering this point and we are also considering this point. In the first method, what we did, we only considered this point. In the first method, we only considered this point because here is where it is rising and touching all that. So we based our modeling in terms of this one. But in the second method, we are focusing on this part as well as this part. We are trying to make it more even. Okay. That's the approach which we are trying. So how do we get that? How will we get it? Okay. So this point over here, which is there during the on time, that is equal to your I peak minus half of your current ripple. That is correct. And this point also is equal to your I peak minus half of your current ripple, because both of them in the average sense are at the same value. But for this case, you're not able to see my pointer or something, or okay, for this point, how do we get the value? We get it from here, we come down to this point. But for this case, from here we come down in this direction. Okay, so that is the method which is used. So let us see how it works. So we have our average inductor current is equal to your I peak minus your, and this is during the time when it is on, I peak minus M1 into dt by 2. But for the time when it is off, right, the main switch it is off, it is again I peak minus M2 into 1 minus d t upon 2. Okay, this is the current. Now, what do we do is we average the current here itself. So we find our average IL current, that is equal to your d into IL dt plus 1 minus d into your IL for 1 minus d t time period. Okay, so that how do we give it as? So we write it as d into your I peak minus M1 dt by 2 plus 1 minus d into your I peak minus M2 into 1 minus d t upon 2. Okay. So how do you simplify this? Can you say? We have many people here. Joshi is there, Parvati is there, Arun is there. How do you simplify this?
From the two terms, we can take I peak together.
Okay, so you take I peak common and you do d plus 1 minus d. So your d and d get cancelled out each other. Okay, this is very good. Next, what should we do?
M1 into d square t by 2
This is m1 into d square t by 2. Nice. Then
minus M2 into 1 minus d square t by 2.
this is minus m2 into 1 minus d square t by 2. Okay. We have got your average IL of t. Now, we have our peak current is equal to this IC minus MC into dt. So this is over here. So we have IL average of t is I peak minus m1 d square t by 2 minus m2 into 1 minus d square t by 2. Okay. So we substitute what is the value of I peak. So this IL of t is equal to this your average IC minus MC into dt minus this m1 d square t upon 2 minus m2 into 1 minus d square t upon 2. So what do we do is we take the d terms common. So you have your MC into dt plus m1 into d square t upon 2 plus m2 into 1 minus d square t upon 2 is equal to your average IC minus your average IL. Okay. Now what should we do? Parvati, what should we do?
Sir, find the value of D.
Okay. D, yeah, we're not exactly finding the value of D, we're finding the value of the D perturbation.
Yes, sir.
Okay, Arun, what do you think we should do?
We can write IL tilde minus IC tilde by using Taylor series expansion.
Okay. What about this D term?
While
Neglect.
taking D tilde, we keep other one constant.
Okay. Okay, so what we would do is we have to, as you have said, Taylor series. So for Taylor series, what would be a better way? What would be a better way? We can write it as, yeah, so this is a part which is problematic. These are single terms where you can just directly put the perturbation. Okay, so we will write your IC perturb minus your IL perturb. This let us call it by a function f. Okay, the function f, which is a function of d, which is a function of m1, which is a function of m2. Right? So this is given by dou f upon dou d into d perturb plus dou f upon dou m1 into m1 perturb plus dou f upon dou m2 into m2 perturb. Any doubts? Can I do this or I'm not allowed? I'm doing some shortcut magic.
Sir, dou F by dou D with keeping other things constant. Is it like that?
Yes, yes, yes. So what we do is we differentiate D. And as you have said, we keep other things constant. So what is your dou F upon dou D? What is that value? So we are differentiating this. So it will become your MC into T. And since they all are constant, we use capital terms. Plus M1T into 2 into D upon 2 plus your M2 into 2 into 1 minus D into minus 1 upon 2. So your dou F upon dou D, that is equal to your MCT plus M1T into D minus M2 into 1 minus D. So now into T. So your dou F upon dou D is equal to MCT plus T into M1 into D minus M2 into 1 minus D. All right. So this is actually equal to 0. And why is it? Because your current, suppose it starts from here, it goes to this value, it comes back over here. Suppose it's in steady state, that is your IL, this point will be same as this point. That time this will be your slope M1, this will be your slope minus M2, right? So in that case, your current, this is your peak in that case. Your peak is what? Your peak is this, let us say this is your IL N, this is your IL of N plus 1. Your peak is IL of N plus M1 into dt. Plus M1 into dt. And your IL of N plus 1 is equal to your I peak minus of M2 into 1 minus D into T. Right? What do we do then? We substitute the value of I peak. So we get your IL of N plus 1 is equal to your IL of N plus M1 into dt minus M2 into 1 minus D into T. Now in steady state, what happens is this and this cancel out because they both are equal. So you get 0 is equal to your M1D minus M2 into 1 minus D, the whole bracket into T. T cannot be 0. That is why your M1D minus M2 into 1 minus D is equal to 0. All right. Your dou F upon dou D becomes equal to MC into T. Would you like me to clarify this once more? Because this is a bit complicated.
So is it like M1 into D is delta IL and M2 into 1 minus D is also delta IL? So it is cancelling.
You're close. Is actually your M1 into DT. T also is there. That is your delta N.
Yes.
Yeah. And yes, you're looking at the correct way. Because this is like kind of like your volt second balance stuff. So they cancel out. In steady state, this will cancel out. Okay. So that's why we get a delta F by delta D is equal to MC into T. So what will be your delta F by delta M1? What will be that value?
D square T by 2.
Okay. And what is delta F by delta M2?
One minus D the whole square into T by 2.
Correct. Very good. So you have your delta F by delta M1 is D square T by 2. And your delta F by delta M2 is equal to 1 minus D square T by 2. Is there a minus sign? No.
So is it a small d or a capital D?
Oh, correct. It's capital D, correct. Good. You guys are paying attention. So this 1 minus D square T upon 2 and D square T upon 2. Okay. So very good. So now we can write our IC tilde minus IL tilde. Dou F upon dou D is what? MC into T into D per term plus D square T upon 2 into M1 per term plus 1 minus D square T upon 2 into M2 per term. So what we can further write is as D tilde is equal to Fm into IC tilde minus IL tilde minus D square T upon 2 into M1 per term. And then you have your minus 1 minus D square T upon 2 into M2 per term. Where in this case, your Fm is equal to 1 upon MC into T. Okay. All right. So should we solve sums now or should we proceed? There are certain sums are there regarding this. Okay. Let us do the sum then. Because we've just studied this theory, let us solve the sum now itself. So this is your question where you're doing accurate small signal modeling under current mode control. This is the first method. You have your input voltage 12 volt, you have your output voltage 48 volt, you have your L is equal to 3.3 microhenry. Your output capacitor is 50 microfarad. Your switching frequency is 200 kilohertz. And we are operating in current mode control. Okay, so what should be the steady state duty cycle?
One minus 12 by 48. So 0.75.
Okay. Let me write. So your question 1. V in is 12 volt. V output is 48 volt. We are doing a boost converter. We have a switching frequency is 200 kilohertz. We have, what is that known? Inductance is 3.3 microhenry. Capacitance is 50 microfarad. And we are doing the first modeling approach. So we have a D. This 1 minus, as you said, it is 1 minus V in upon V out. So what is that value?
0.75.
Okay, it is 0.75. So we got our duty. This is a very simple thing. Duty I found out. Now, this is a boost converter. So as we have asked, what are the slopes of the inductor current? So what are the slopes? Can you tell?
During on time, it is V in by L. M1 equal to V in by L.
Okay. Okay, I think Parvati is also working on boost, right? So let her tell what is the falling slope then?
V in minus V0 by
Okay. Okay, when Joshi is saying it is V in minus VL upon L, and Parvati, what did you say? Can you repeat again? Okay.
V in minus V0 by L.
Okay, okay, okay. Both of you are saying same thing. So you are saying it is V in minus V0 by L. So let us look at it. Let's see the boost converter. This is your boost converter. You have your input is over here. You have your inductor is over here. This is your main switch, which is the MOSFET. This would be your diode, right? This is your capacitor. This is, sorry, capacitor. This is your load resistor. This is your V0. So now, what are we focused on? We are focused on your current, IL, right? So if you see at the left side, and let me say at this point, and your ground, this is your ground, right? This is your ground. So the voltage at the left point, let me name it at some value. Let us say A, and this is B. Okay. So your VA, that is equal to V in. It will not change at all. It will always remain at V in. If your V in changes, VA will change. Otherwise, it will be at V in. Okay. What is the confusion is here? What is your voltage at VB? Okay. What is your voltage at VB? So suppose your Q is 1. Then what will be the voltage at VB? In the ideal sense?
Zero.
Yes. 0. Okay. And when this is when Q is 1. And when Q is 0, what will be your VB?
V output. V0.
V0, right? So your VL, that is this voltage across your inductor, it is equal to your VA minus VB. Okay? I'm spending time here because this is a source of confusion. Okay, so this is your VA minus VB. Now, that actually is equal to your V in minus 1 minus Q into V0. Okay, let me not complicate it further. So your VL is equal to V in when Q is equal to 1, and it is equal to V in minus V0 when Q is equal to 0. Right? And as you all have rightly given your answers, your M1 is equal to V in upon L. Or let me not say M1, let me call it M rises. Rising slope is V in upon L. And your falling slope is when your inductor current is falling, that is equal to your V in minus V0 by L. So this you all have told correctly. So you all know the boost converter well, you're telling it correctly. But there is a slight thing which you have to keep in mind, right? That could change the polarity of your answer and that could change your MCQ correct answer as well. Okay. So we have done this. We have found that the voltage across the inductor is V in when it is switches on, and it is V in minus V0 when switches off. So your current, it will rise like this when your switch is on, and it will fall like this when your switch is off. So this slope, which we write it as, this slope is your M rise, this slope is your M fall, which you guys also got correct. But when we have done the modeling, instead of M fall, what we wrote it as minus M2. We are not using M fall there. If you notice, we are using minus M2. And you would have to change, so what would become your M2? Your M2 would be equal to V0 minus Vn by L. This is how we are writing it. So if to make it better, more clear, let us look at the numbers. So we have told Vn is 12 volt. Let us say your L is L. Okay, let us say L is L. So we have seen your M rise is equal to M1 is Vn upon L. So your Vn is 12, L, let it be any value. So this is 12 upon L. What is your M fall? Can you tell me? Since my output voltage is 48 and input voltage is 12, so what will this be?
Minus 36 by L.
Okay, correct. Minus 36 by L. But your M2, as is being used in your modeling, your M2 is equal to your minus M fall. So that is equal to 36 by L. Right? So when we are doing the modeling, what we prefer to do is, why we have used the opposite notation is, we want to say that over here your current is rising. So this is your M1. It is clear. It's positive. It will always rise. That is very clear. But in the case of the falling slope, if you notice, we want to signify that it is falling. So we use a minus sign. And we use minus of M2. Okay. We are always making sure that the magnitude of this and this magnitude is positive. So in this case, we don't need to change the sign. But over here, we are using minus M2. We say that this is a negative slope. So to signify that, we are doing this math. Okay, so any confusion in this? You want me to repeat it again? I can repeat it. Okay, so this what I want you guys to know for sure, right? You have to be very careful about this because this is the approach which sir has considered in this course. And like it or not, in your exams and everything, teachers usually give marks if you go through their steps and their methods, right? So you could do all this modeling by considering M fall itself, but then you'll have to change the sign, everything. But as sir has done it in this method, and as the questions also have been framed based on this method, I'd want you to make sure and be cautious that your M2 has been defined in this manner. Okay. So if it's a buck converter, if it's a boost converter, or if it is a buck boost converter, you follow this approach. And this approach which I showed of these nodes and finding out, this would be very useful if you have a buck or boost or buck boost. This would work in any of those cases, right? Okay. So very good. You have understood this. So where did we deviate? Okay. Slopes. We were talking about the slopes. So that's why your M2, as per Sir's definition, your M2 is actually equal to V0 minus Vn upon L, right? So now, what you have to do now? What's the question? Yeah. When we also just did this derivation, I think by now you should know the derivation very well. You have seen Sir do it, you have seen Teja do it, you have seen me do it. So you should know the derivation well. So your d perturb t is Fm into Ic perturb t minus Il perturb t minus dt upon 2 into M1 perturb. Right? So we have, in the first modeling approach, we have our Fm is equal to 1 upon mc plus m1 upon 2. Okay, you could either remember this or you could derive it in the exam as well. Many times it's hard to remember everything. So if you know how to derive it, it is good. But if you want to work fast and everything, you can derive it as well. So this is your Fm. They have told your d perturb is equal to Fm into Ic perturb minus Il perturb minus what they have given here. We just derived it, but you forgot. I forgot. So then minus dt upon 2 into M1 perturb. So in a boost converter, as you all have told, M1 is equal to Vn by L. So we just have to replace it over here. We get our d perturb is equal to your Fm into Ic perturb minus Il perturb minus dt upon 2L into Vn perturb minus 0 into V output perturb. Okay. So this perturbation of output voltage does not affect in this modeling technique. So then you would have seen questions are asked like this: Fm into Ic perturb minus Il perturb minus K1 into Vn perturb minus K2 into V output perturb. So accordingly, you can get what is your K1, what is your K2, right? So this way you can do for this approach. Let us say we go for the next question. In the next question, they have used the second method. Second approach has been considered. They have taken the average current when it is on, the average current when it is off, right? And then they have done the perturbation, everything they have added. As we have seen Taylor series, etc., all that was done. And it comes out in this expression. So very well and good for you. They have provided the expression already. The expression has been provided to you. Now you have to find it in terms of this. And since you are working with a boost converter, you must know what is your M1 perturb, you must know what is your M2 perturb, right? So let us do here. This is your question 2. They have told your D perturb is given by Fm, Ic perturb minus Il perturb minus D squared 2 T upon 2 into M1 perturb minus 1 minus D squared T upon 2 into M2 perturb. So, as we discussed extensively, what will be your M2 perturb? Have you forgot so fast? What will be your M2 perturb?
V0 tilde minus V in
V0
tilde by L.
minus
Okay, correct. So it is V0 perturb minus V in perturb by L, right? That's why your D perturb is equal to your Fm into Ic perturb minus Il perturb minus of, let us say V in perturb over here. L also will take common, T2 also will take common, T also will take common. This is D square minus 1 minus D square. And this is minus V0 perturb 2L T on 1 minus D square. Okay, so can you simplify what is D square minus 1 minus D the whole square? What would be that value?
1 minus 2D.
Would be
1 plus 2D, sir.
should be 2D minus 1, right? Because I'm saying the minus v in per term is there. Let me write
Yes,
it.
yes. 2D minus.
Okay. 2D minus 1.
Yeah, correct. This is IC per term minus IL per term minus v in per term t upon 2L. Yes, you have told it is 2D minus 1 minus v output per term 2L t into 1 minus d square. Because the questions are framed, it is like minus k1 into v in per term minus k2 into v output per term, right? Accordingly. So that's why you must be very careful about the signs. Very, very careful, right? If you switch the signs, you have done all of it correct, but you have messed up in the signs. But MCQ, you don't have steps for marks. Okay, so there you'll be the loser. So you must have a very clear head and do. And don't work in open loop. Okay, that many people, I don't know, at least I've come across a few people, they'll just answer everything and they'll leave it. They'll not check again what they've answered. So it's my recommendation, once you luckily and if you're fast and good, you would have solved the questions. Maybe some time would be left in your exam. I would recommend you go check again the question and what answer you have marked, what answer you have calculated and done and do. Okay. You re-verify and check again. You must be very careful. Yeah. Because silly mistakes cost a lot in exams, especially in exams. In maths also you have seen, and in exams also silly mistakes cost a lot, right? Okay. So we have done these two questions. You guys have done it. Now let us see. Okay. What is the transfer function of a boost converter in current mode control? So what of these things are correct? What do you think is correct? What do you think is wrong?
First one is correct.
Okay.
First order.
Okay. First order, good.
Then KDC is R into 1 minus D by 2.
Good.
So it is load dependent.
Yes. So does load dependent and duty ratio dependent. Okay.
Then RHP0 is that depends on R and D. So it is not fixed.
Okay. LSP0 is not fixed. And Joshi, C is correct or C is wrong?
C is wrong, I
Okay.
guess.
Okay.
Then we have boost converter transfer function. There is a ESR0 and RHP0 on the numerator.
Okay.
And we have one pole on the denominator.
Okay.
So our controller should have an integrator.
Mm-hmm.
Then 2 poles to cancel those two zeros.
Okay.
And there should be a 0 to cancel the control plant pole.
Mm-hmm.
So it is not PI controller, I guess. I think.
Yeah, it is not a PI. Hmm. Okay. So, yeah. So, Joshi, I hope it is clear to you, or let me provide further clarifications. So, we are doing question 3, although the numbering is different in the PPT. So, what we are discussing is the transfer function for a boost converter. So, we have your GVC of S is KDC into 1 minus S upon omega RHP into 1 plus S upon omega ESR upon 1 plus S upon omega P, right? What we do is so first is the DC gain is load dependent because your KDC is R into 1 minus D upon 2. So there's the factor of R plays a very major role. So that's why it is load dependent. Next is your omega RHP is R into 1 minus D square by L. So R is again playing a factor. If R changes, D changes, it will change. So it is not fixed. Then it's first order, right? Approximately. And PI controller. Okay, so we have a GC of S we need. We select GC of S such that it is 1 by S. You need an integrator to make your steady state error 0. Then you place one of your controller poles in coincidence with your RHP 0 to reduce that effect. Like, so that the gain effect of both is cancelled out. Then you could place a pole to cancel out your ESR 0. In some cases, you neglect your ESR 0, then you will not need this second pole. And then you would place a controller 0 to cancel out this pole. So what would you do? You place omega CZ is equal to omega P. Omega controller pole is equal to your omega RHP. And your omega CP1 is equal to your omega ESR. Okay. And you'll also have what is known as your KC, your controller DC gain. This KC also is important. Okay, so that's why this is not a PI controller. This is a higher order compensator. All right, so PI controller is not sufficient for the boost converter in under current mode control. You need a type 2 or a higher order compensator. Okay, so let's proceed to the next part. Current mode control. What statements are true for current mode control? All of you can answer. Joshi also, Parvati also, Arun also. All of you have become speechless. Can tell some. What do you think? Think out loud. That's important. Because when you think out
Sir,
loud, it helps me to understand what is your understanding. Yeah.
sir, in voltage mode control,
Mhm.
boost converter has 2 poles.
Yes.
But here we are treating the inductor current as a constant, like modeled as a current source IC.
Yes.
So that pole is absent, is pushed to infinity.
Yes, very good. So that's my first statement A is true. Okay, good. Next.
And since it is first order, it is easy to implement.
Okay. Okay.
And we don't have V in term on the gain like voltage mode control. So it is audio susceptibility is good.
So current mode control.
In voltage mode control, I think V in was there in that gain term.
Yes,
Here
correct.
V in is not there.
Okay.
So it is independent of input.
Hmm.
Controller gain is independent of input voltage.
Okay,
So good audio susceptibility.
correct. So that's good audio susceptibility. Good.
Then since it is load dependent, we need load feed forward to improve the performance.
Yeah, fantastic. You got it right. Yeah. Okay. So I think the ladies are not answering, but let's see. So let me just recap what Arun has stated. So one is current mode control. Your inductor is behaving as a current source, as a controlled current source. That is the way we want it to behave. So that will push the pole to a very high frequency, the inductor pole, right? Now, since it is current mode control, the approximate transfer function is first order. So it is easier for you to design the controller for it. Then what else was there? Okay, current mode control, if you will see this expression over here, it is dt upon 2L. Okay, and this, if you calculate, it will be very small. It will have negligible effect. Further, if you would see this transfer function which was given over here, that is this one, it is independent of Vn. There's no dependence on Vn. So in an approximate sense, current mode control has very good ability to reject disturbances in your input voltage. Okay, that is why it has good audio susceptibility. Okay. The last one is current mode control with load current feed forward offers good response. So current mode control is dependent on it is affected a lot by what is the value of your resistance. That is what is your load. But feed forward will, what it does is it will sense what is your load current, and based on that it will change your control command such that you will adjust. It will give you not prior information, it will give you the on the spot instantaneous information that your load current has changed, and since your load current has changed, your inductor current also has to change, something like that, right? So it is providing additional information which makes your whole loop independent or less dependent on your value of R. That is the advantage of load current feed forward. Okay. And sir has also shown it in simulations as well. Okay. Any doubts in this? Or Arun's explanation was very good. You all don't have any more queries. Okay, so we'll proceed to the next question. Question 3. Okay, average current mode control. What are your thoughts about average current mode control? Have you heard of it? What do you think of it? And this time we'll ask, okay, Parvati Joshi, you can please answer. We'll give you the opportunity and the chance. So what do you think of this question? What options are correct and what options do you think are wrong? No answer. Any silence? Yeah, silence is golden, but not always. Yeah, Joshi has told something. Okay, one is wrong. Okay, good, good. You're correct. Further. Okay, Parvati is saying C is correct. Good. Joshi has told that A is correct. Okay. What about the remaining B and D?
B and D are correct.
Okay. What about others? So we have told that A is correct. Average current mode control has a faster response than peak current mode control. That is not correct. Okay. 2 and 3 are correct. Joshi is saying 2 and 3 are correct. Okay, average current mode control allows us to use cheaper currents and amplifiers. Good. Loop control also is good. Okay. So I'll say B and C are correct. Correct as Joshi has told. A is incorrect and D is incorrect. Okay. So let us see how it is done. So we are going for, let's go to next page. So we are considering average current mode control. Okay. In average current mode control, what we are doing is this is your inductor current, right? We want to control this average. But in peak current mode control, what we are doing, we are controlling this peak. We are controlling this peak. And indirectly, we are trying to control the average. But in some cases, that's not good. Like if you have what is known as your power factor correction circuits or in your battery charging circuits, you want to have a specific control over the average value. In that case, you should not use peak current mode control. You have to use average current mode control. So what happens in average current mode control is your inductor current, this inductor current goes through what is known as a low pass filter. Okay. And that will filter out and give you like your IL average, sense IL average. Okay. So you have your reference average current which you want, that you subtract it from your IL average sensed value which you're getting through your low pass filter, which is could be your current sense amplifier. So you have a current sense amplifier which is sensing your inductor current and it is giving your IL average sense. So that means your bandwidth of your current sensor would be low. Okay, would be low. Now if your bandwidth of your current sensor would be low, then it would improve your, then you will get the average value. So it could be cheaper. Your current sensor could be cheaper. Okay. So this is one point. Next, you get your current error. You get your current error that you will pass it through a PI controller that will generate your command signal, which is compared with, you have some ramp, your sawtooth ramp you have, that generates your duty. Q and duty it generates. That goes through your GVD, which generates your V output. Now, in some cases, you just don't want to control your reference current. You want to control the voltage as well. So you'll have a reference which you subtract from your output voltage that is passed through a controller which generates your I reference. Okay, so you would have, this is your inner current loop and this is your outer voltage loop. So should your IREF change fast, or should IREF which is generated from your outer loop change fast, or should your this command signal change fast which is generated from your inner loop? What do you think?
Inner loop should be faster.
Yeah, inner loop should be faster. Okay, and it should be at least 10 times faster. That's the thumb rule. You want your inner loop to be at least 10 times faster. So that they don't interact. That is what happens is, if you're trying to control your current, you're trying to reduce this error by changing your command signal, but suddenly this reference itself changes faster. It changes more fast. So then this will change fast, and this also will have to adjust. The error will further increase. So you don't want that. So what you want, you have to have an inner loop which is faster and an outer loop which is much slower. Okay, so if you would see the question, I intentionally framed it in such a manner that I wrote that the outer loop should be 10 times faster, but that is not correct. The outer loop is your voltage loop. It should be 10, it should be at least 10 times slower than your inner current loop. Okay. And as you have told, it is a two loop control. That is very good. Right? So any queries till this? Or I'll proceed to the next question. Okay. You guys are very good. Let's go to the last question. Current mode control design. We want to design using current mode control. So we have some input voltage, output voltage, load resistances, inductance, output voltage, output capacitor, switching frequency. We have to operate in peak current mode control. I should have mentioned here, it should be peak current mode control. So what is the steady state duty cycle in this case?
Point 0.6.
Okay. Okay, Joshi, you also correct, 0.6. Okay. Now what should be the bandwidth of this controller? What do you think should be the bandwidth?
Minimum value of that 1/10 of switching frequency and RHP 0/3.
Correct. It should at least be minimum of omega RHP by 3 or 1/10 of your switching frequency. Okay. Yes. So you guys are using MATLAB or you're not using it? Hmm? No one is answering.
In the initial weeks, I simulated, but later it was not able to complete the simulation
Very, very difficult, yes.
because it is taking time to watch the videos. Also.
Yeah. Also, it's like kind of like a hack. You can, instead of manually writing the code, you can even copy the code. It is, let's say, MATLAB is very slow here. Okay. So if you have Windows 11, right, you just have to take a screenshot or something. You guys may know this by now, but just in case you don't know, I take this screenshot and then I can, oh, this is Windows 10. So my laptop is Windows 10. That should be an option. No. There is an option. So this is Windows 11 only. This option is there. This option here. This will enable you to copy the text. So wherever some PDF, some cases, and MATLAB code, then you can take the screenshot and you can copy the text and you can paste it. You don't need to type text all over again. That's a useful way. You can save time. That's something you can do. Why is it so slow? Just hold on. It's very slow. Let us just use this pen paper approach. It's taking lots of time. So question 6 is we want to find the bandwidth, right? So they have told R can change between 30 to 300 ohm. And your D, as you have told, is 0.6. Your L is 3.3 microhenry. So what is the range of omega RHP? Let us say there's omega RHP 1, omega RHP 2. This is your R1, this is your R2. So can you tell me these values? What will be omega RHP 1? What will be omega RHP 2? And calculate and tell me.
Sir, for 30 ohm, it is 1.45 into 10 raised to 6.
Okay, 1.45 into 10 raised to 6. Okay, this is in radians per second. Convert it into hertz.
Divided by 2 pi.
Yes. Divide by 2 pi.
231.49 kilohertz.
Okay, so this is 231 or plus at 0.5 kilohertz. Okay, this is your omega RHP 1. What will be omega RHP 2?
It is 10 times because
Yes.
30.
So it will be 2315 kilohertz. Yeah? So it is 10 times. Okay. They have also mentioned your switching frequency is 200 kilohertz. So what is your FSW by 10?
20 kilohertz.
Yeah. So which bandwidth should I use?
The minimum is 20.
So we'll have to go with 20 kilohertz. Okay. Any queries about this?
Sir, just to cross check, I used the formula R into 1 minus D square by L
Correct.
for
That's the
omega RS.
formula. Yes. That's the formula. Right. In this case, your L is actually very small. That is why your omega RHP is very high. Yeah. Okay. So So we have a new participant today, Joshi S. So it would be good if you could introduce yourself. Because Arun has already talked to me. Arun is from NIT Calicut. Parvati is studying in Chennai in some college. So Joshi, what are you doing? Like, are you a faculty? Are you a student? Are you a PhD scholar? Or a working professional? You could let us know.
Sir,
Tell.
2315, how to get that value? How he, I
That,
got 1.4 into 10 power 6.
okay, I have not checked it. He told it is
This,
this formula, right?
yes, sir.
Okay.
So it was 1.45 into 10 power 6 in radians per second. Then you asked to tell me in
Hertz, yes.
hertz.
So that you have to divide by 2 pi if you want it in kilohertz.
Okay, sir. Okay.
Okay. Okay, so Joshi is third year BTech student. Okay, very good. Okay. And from which college? Okay. Yeah, so I told to convert into kilohertz because switching frequency also is in kilohertz, right? To make it easier. So this actually should be FRHP1. And this should be actually FRHP2, sorry. If we are doing in radians per second, we use the term omega. If we are doing it in hertz, we use frequency F. Okay. So this is the convention. Yeah. So I think MATLAB is really very slow here. My laptop. Let me just show something else. So this is one current sensor which I was looking at. Okay. You could notice. So this current sensor is by analog devices. We put it over here. This is the current sensor. So when you're selecting a current sensor, you want the bandwidth to be very high. It is like around 2.7 megahertz. And it should usually be at least 10 times your switching frequency. So you want the bandwidth to be high. Common mode voltage is what voltage it can withstand. So wherever your current sensor is placed, it will experience some voltage. Like if you see your boost converter, we had already drawn it. Let me go back there. Where's the boost converter diagram? Here. If you want to measure the current, right, you would put some sensor over here. You would place a sensor over here. Right? You could place it here or you could place it over here as well. Assume we place a sensor over here. So there is a sensor. Okay, it's a current sense amplifier. So the current inductor current will flow through it and come out and then flow over here. So what will be the voltage which would be seen over here? What is the voltage which it would experience with respect to the ground? What is the voltage it would see?
Sir, is it connected across a series resistance or?
Yeah, so there could be a series resistance and then followed by an amplifier, or certain amplifiers have that resistance internal. So your certain like either it could be you have a series resistance, and then you amplify this, or in certain cases, this it will go to your current sense amplifier. The current will go in and come out like this, in this manner. Both cases are there. So in both cases, whether there's a series resistance or it flows through the current sense amplify the current, what would be the voltage seen at this point? That is my question.
Almost zero, close to zero.
So you're talking in terms of, you're right if you're considering this voltage. If you're considering this voltage, it would approximately be zero because your current sense resistance would be very low. Let us use numbers. Let us say current sense resistor is 1 milliohm. Let us say your current flowing is 10 ampere. So this voltage difference will be 10 ampere into 1 milliohm is how much? It is 0.01 volt. Okay, 0.01 volt. So it's approximately 0 volt. You're correct in terms of saying the voltage across the current sense amplifier. But I am talking of what is the voltage at this point with respect to the ground. What is the voltage at this point with respect to the ground? That's what I'm asking.
That is V in.
Yes, correct. It is V in. And as you have correctly pointed out that the difference is almost 0 volt. That is the voltage over here as well as the voltage over here. Both are approximately V in, right? So in our case, our V in is 12 volt. That is quite low. But in the case of, as I don't know what you guys are working on, what is your research, and Joshi is in third year BTech and all that. So your application might be different. Your voltage might be very high. And when you're selecting the current sense amplifier, you must make sure that it can withstand that voltage. So that is this voltage which is written over here, the common mode voltage. Okay, this is your common mode voltage. Next is you have a gain. That is whatever small voltage you apply, that approximately 0 volt voltage, that has to be amplified. If it is not amplified, then by noise or by various other things, it will get distorted. So you need an amplification. In this IC, that gain is fixed 50 volt by 50 volt. But in some ICs, you can change it or by changing certain resistor, etc. There are various possibilities are also there. Okay. Slew rate is like how fast this output can change. That is one of the slew rate. That is dependent on the voltage and various other factors as well. Okay. So these are some important things when you guys in your projects, in your work, you would be selecting a current sensor, etc. That's why. So this I brought up because Sir told that in average current mode control, the bandwidth of your sensor should be low, could be low, right? So that's what I just wanted to show a practical sensor as well. Okay, any doubts in this?
Sir, what is the current that it can measure? This IC.
To check, I have to check. Let me just see. Just see. Just say D84118. Can measure to be given. This is not given data sheet. See. Mhm. Okay, it has a shunt resistor. So in this IC, you have a shunt resistor followed by, and the voltage across the shunt resistor, it would amplify that. So this will have an output which is maximum, let us say around 5 volt, right? So that means the input voltage of across these two terminals, that should be 5 by 50, less than 5 by 50. So 5 by 50 is 100 millivolt. So as long as your voltage across these terminals is less than 100 millivolt, that much current it can sense.
Okay, so based on that, we will select that shunt resistance.
Yeah. Based on that, you select your shunt resistance. It's not this straightforward. There are various things also there. But here, if they have seen, they have shown minus 50 to 50. Current is going from minus 50 to 50 ampere. So, is it clear? This one? Minus 50 to 50 ampere.
Yes, sir.
Yeah. So at least till that you can run it. Just to that. There are various other things are there. Yeah. They show some test results also. They show, right? They say how it works. The theory of operation also is explained. How do you select your shunt resistor? That also they have explained. Your shunt resistor should not be too small, as the voltage developed will be very, very low at very low current. So it will be affected by the offset and noise, etc. Also, your resistor should not be too large, otherwise your losses will increase. And it can have some offset, etc. All those things are there, right? It has an application circuit where it can be used. They've shown. Also, they have written filter. Sometimes we have to add a filter as well to filter out some noise, switching noise, etc. So details about what the input filter also has been mentioned over here. Okay. So all these things are there. You can check it out as well. Right. Also, we can do what is known as the spice simulation of that as well. Like if you see, like here I had made us the schematic in LT spice. The model also was there, and I had simulated it for a boost converter or something. Right. So you can also do all these things and test. Like I think you guys will have to make some boards for your research and project, or you would have already made as well. So for those things, such things would be useful and in handy. Right. Okay. So any other queries, doubts? Something you'd like to mention or say? Uh, are you able to see the assignment solutions? Has that matter been resolved? Hmm? Regarding
With
assignment?
finding the gain crossover frequency. Can you explain a little bit?
Which one? Which one?
Finding the gain crossover frequency.
Okay. Gain crossover frequency. Okay. Yes. Actually, I wanted to explain with MATLAB, but MATLAB is not working actually today. It's like very terribly slow. Okay, you are saying gain crossover frequency coding. Okay. Yeah. So gain crossover frequency, right?
Yes, sir.
Yes. So let's go for a simple example. You have a boost converter GVC of S. That transfer function we have some KDC into 1 minus S upon omega RHP into 1 plus S upon omega P. I'm neglecting ESR 0. Okay. Next, you have your controller. It is DC gain of your controller to 1 upon your omega controller 0 to cancel this pole, an integrator, and a controller pole in coincidence with your omega RHP. Okay, so you get a loop. Your loop transfer function, L of S, is GVC of S into GC of S. That is equal to your KDC into 1 minus S upon omega RHP upon 1 plus S upon omega P into Kc into 1 plus S upon omega controller 0 into S into 1 plus S upon omega controller 4. So as I told, this and this get cancelled, right? So this and this get cancelled, and your omega Cp is equal to omega RHP, so it gets written as KDC into Kc into 1 minus S upon omega RHP upon S into 1 plus S upon omega RHP. Right? This is the method which sir has shown. So now you are interested in finding the crossover frequency, right? So this is your L of S. We substitute S by L of J omega. So that is equal to KDC into Kc upon J omega into 1 minus J omega by omega RHP into 1 plus J omega upon omega RHP, right? Let us find there. So this is a complex number. It's a complex thing. It has a, okay. Hopefully the disturbance doesn't affect you. They're playing football down. Okay. So this is a complex quantity. It has a real part. It has an imaginary part. You can also write it in like this is your real part. This is your imaginary part. This is your real part. This is your imaginary part. You can also write it in terms of a magnitude and phase. So you write L of J omega, the magnitude. What is the magnitude? KDC into Kc upon omega into square root of 1 plus omega square by omega RHP square upon square root of 1 plus omega square by omega RHP square. That is why sir has placed your pole at omega RHP. What is the advantage with that? The magnitude part gets cancelled. So you get it to be KDC into Kc on omega. This is the magnitude of L of J omega. This is done, but the work is not over till now. We have to find angle of L of J omega. So what is your angle of L of J omega? So that would be your minus tan inverse of this angle, that is omega upon omega RHP, right? So this is your numerator part. You first write in terms of the numerator angle. Since this is minus, so we put a minus tan inverse of omega upon omega RHP. Then minus of your denominator contribution. J contributes 90 and this contributes tan inverse of omega by omega RHP, right? So your angle of LJ omega is actually minus 90 minus 2 times tan inverse of omega by omega RHP. Okay? Till this part, is it clear?
Yes, sir.
Okay, good. So now you have your crossover frequency. You're worried of your crossover frequency, right? So this is a term which is used a lot. That is your crossover frequency, which is symbolic of your bandwidth. At that frequency, you have a L of j omega c. This magnitude is equal to 1. This is where your magnitude is equal to 1. So for that to happen, you know what is it? It is kdc into kc upon omega c. So this is your kdc into kc upon omega c. So from here, you can design your kc. So you design your kc is equal to omega c by kdc. This is a design way we can design the controller gain. You can design the controller gain based on your crossover frequency. Next, you have got it for the magnitude, but what about the phase? So we substitute angle of LJ omega c at that point is minus 90 minus 2 tan inverse of omega c by omega RHP. Okay. Now what is your phase margin? Your phase margin is actually 180 plus your angle of L of j omega c. At your crossover frequency, you find your phase margin, right? So that if you compute, it will be 90 minus 2 tan inverse of omega c by omega RHP, right? This is good. Now, what would happen if your omega c is equal to omega RHP? What would happen if your omega c is equal to omega RHP? What do you think will happen?
0.
Very good. Your phase margin will be 0. What would happen if your omega c is what is omega RHP by root 3? What would your phase margin be in that case?
30 degree.
30.
Correct. Very good. Right? So from this, we know that your omega c should be less than omega RHP. Good. Now, for a good design, we say the phase margin we design for around 45 degree to 60 degree. Okay. So accordingly, we will find out what should be a crossover frequency. So while designing, there are two ways. You go from your phase margin and you get your crossover frequency, or you go from your crossover frequency to get your phase margin. So that's why we had a question. We went from the frequency. We told that this is your omega RHP, this is your switching frequency. So we use the thumb rule that it should be the minimum of omega RHP by 3 or omega switching frequency by 10. That we used. But in case they say the phase margin should be this much, then we have to find out your omega c, that is your crossover frequency. Okay. Any more doubts in this, or is it clear? Okay. Let me know if you have any more questions or queries. MATLAB seems to be working. So let us just try. Suppose your R is 30 ohm, L is 3.3 E minus 6, C out is 50 microfarad, switching frequency is 200 kilohertz, T is 1 upon time period is 1 upon FSW, right? V in is 12. V ref output is V out is 30. So your D you get it by 1 minus V in upon V out. This is your duty. Okay, this is your duty. The duty you get it as 0.6, right? Now you have to get what is your omega RHP. Omega RHP is R into 1 minus D raised to 2 by L. This is your omega RHP. Your omega pole is 2 upon R into capacitor, that is your output capacitor C out. Your DC gain is R into 1 minus D upon 2. This is your values. So let us find the transfer function. So S is equal to transfer function of S, and your GVC is KDC into 1 minus S upon omega RHP by 1 plus S upon omega whole. Let me run it once. How does it look? This is your transfer function. So this is your transfer function, minus 8000 S plus 1.164 into 10 to the power 10 upon 1.445 e power 6 plus 1.939 e power 9. This is your transfer function. Now you have to find your controller, right? Controller has some KC. Okay, first let us find the body form. Figure 1, body of G underscore VC. Let us draw it. Let us run it. Okay. So actually this properties, it should start, phase should start from 0. Let us do that. This will graph phase, adjust phase offset to 0. And the limits of frequency, let us go from 0.1 to switching frequency is 200 kilohertz. So 200 E3. Okay. So this is our body plot. Okay, it is starting at 0. It will soon settle at minus 180. It will soon go to minus 180. And this is your DC gain. This is your DC gain part. And then it is falling. It is falling. Okay.
Sir, for adjusting the phase axis, what you have done, right clicking on.
Right clicking there, let me show. So properties, options. I adjust phase offset at 0. That is, phase should start at 0. So around frequency 0, it will try to make sure phase is 0. Earlier it was phase is 360. 360 is 2 pi, which actually is 0. Right? So that's what they use. Sometimes MATLAB makes the
Okay.
issue, so you run this. You can
Okay.
code this also, so that you don't have to manually do this, but I'll not show it here. This is your Bode plot. I think the mistake I have done. What I've done is I've reduced the range very small. Let us make the range 2E8. Something like this. So what is happening is you have over here, around over here somewhere, your pole effect is coming. This is where your pole is then, so it starts falling. So you have a DC gain, then your pole is falling. And then over here, your zero effect starts coming. So that's why your DC, that's why your magnitude gets sort of fixed. It gets sort of fixed. But in the case of your phase, your pole causes it to fall, settle on minus 90. Then your RHP zero effect comes and your phase again further falls. So that is the what you say, the challenge with RHP zero is it will bring your affects your gain plot as well. But instead of boosting your phase, it reduces your phase further. That is the problem with RHP zero. That is one of the issues. So this is a challenge. Next is I'd like to show you the step response of GVC. Okay. Let me evaluate the section. Right. Oh, is running it. So this is the step response. If you will notice, it finally settles at its DC gain. DC gain would be around 6. Okay. And if you will see this initial part, initially there will be a dip. You know why it's not showing the initial dip? See here. Okay. Let me change the scale. Yeah. Be slow today. Sorry. Yeah, it's coming. So your X limit, let me make it 0.005. Okay. You make it 0.001. Okay, okay. The RH zero effect is very negligible in this case. That's why it's not visible. Yeah. Otherwise, what would happen is to uh, when you give a step input, it would actually output would actually dip and then it will rise. Then it will rise. So this one is due to your omega RHP. But for the values which we have taken, your omega RHP is very high. So this dip is very small. It was not visible. Okay. Yeah.
Sir,
This
if
is
instead of
correct.
3.3 microhenry, if we use high L, maybe.
That yes, that also we can do. Let us make it 3.3. Make it 33 or something. 330, let us make. To run it now. So a bit slow. Okay, let us. Okay. Still not showing the dip. Not to understand why. It is not starting at 0. to check this. Okay, I'll check this and see, but usually what will happen, it will start from 0, it will dip and then go. Here instead, MATLAB is plotting it as though it is starting from a negative value and then going up. Okay, this part I'll have to see. Right, it's showing like this. Then I'll check. Okay. So let me just say one final part and we'll complete it. So this you have got your transfer function, everything. Now you have to design your controller, right? So controller design. So let us go back to original 3.3. So your controller pole will be at your omega RHP location. Then what else is there? You have a controller pole at omega RHP location. Your omega controller 0 is at your plant pole location. And your KC, we have to design. Let us take KC for the time being 1. Okay. So your controller is KC into 1 plus S upon omega controller 0 divided by S into 1 plus S upon omega controller pole. This is how your GC is. Okay. Now, your loop L is GC into your GBC. That is your plant transfer function. Okay, now, let us make figure 4. Bode of GBC, that is your original thing. Hold on. Bode of your controller, that is this. You hold on. And your bode of your loop, that is 2. Let us just plot it, how it looks. With controller KC, let me make it. Okay, let us do it to see how it looks. It's running. Okay. Let's add this. So insert legend. So GVC is your plant transfer function. GC is your controller transfer function. And L of S is your overall loop transfer function. Let us. So what has happened over here is it has started from 360. It has again made a mistake and plotted from 360. That it should not have done. Further, because your DC gain of your controller is small, it is starting from less than 0 dB. That also should not be done. So let me just change your KC. Let me increase it. KC, let me make it 1E3. Let's just check how it works. Let me run this section. Okay. So, okay. So just come. Let me adjust the offsets in the face. Properties. Properties. Adjust face offset at 0. So it is done. It starts from 0. So insert your legend. All right. So now let us see the stability margin. So okay. So we are concerned about your loop, right? If you will see the loop, phase margin is given 89.5 degree, approximately 90 degree. Your frequency is 6C03 radians per second. Okay. Now what we can change is we can change the DC gain. That gain KC we can change, and that gain KC will actually change your omega C. and that will in turn affect your phase margin. So let us try one more case, right? Let us change Kc from 1E3. Sorry. Let us make it 1E2. Just one try. Let us run it. How it looks. Did it run? No, it's come. Okay. So now, what is your loop? Is this blue one L? Okay, that has further reduced. So phase margin is 60, but the frequency has reduced further. It has become 600. Okay. So accordingly, you can change it, and as per Sir's criteria and formulas, you can get the exact omega C, exact phase margin, all those things also you can do. You can also try that. Oh. Okay. So any queries regarding this?
No, sir, it is clear.
Okay, okay. Okay. Thank you for patiently listening. Hmm? Yeah. Okay, then we can end the session. Good night.
Thank you, sir.